Hello, everyone at home. Welcome to another Wednesday evening, coming to you from Cambridge University Astronomy. Those of you that have been coming for our Wednesday evenings for a while will know the drill already. During this period of COVID strangeness, we're doing our Wednesday evenings online. We're very happy to say that we have a clear evening today. So we have a nice double bill of talk about some fascinating astronomy, and then we're going to be going live to the Cambridge Astronomical Association, who are going to be doing some stargazing. I think they have their telescopes on the moon and some galaxies last time I heard. Before that, I'm very happy to introduce our headline speaker. We have Joanna Piotrowska, who's going to be telling us all about why black holes won the Nobel Prize and why exactly we should care about that. So yes, over to you, Asha.
Thanks a lot, Matt, for the wonderful introduction. Hi, everyone. Hello, everybody on the other side of the long Ethernet cable. So yeah, let's talk about the Nobel Prize and black holes, which won the prize this year. So in order to talk about that, we need to, if I get my buttons right, set the stage. So we have to ask the question of what black holes really are. For those of you who have been watching this series of talks or coming to the Physical Institute for months prior, will have heard about everything about black holes, from the smallest one to the biggest ones. But for those of you who are new, let me quickly set the stage. So in order to do that, we have to have a quick recap of general relativity, essentially showing you the Einstein's equations on the slide, but that's irrelevant. What relevant is that in 1915, Einstein published work which essentially set an equality sign between the curvature of spacetime and the distribution of mass. And what I mean by this is that gravity no longer demonstrates itself as this spooky action at a distance, well, force at a distance, as in a Newtonian understanding, but actually three spatial dimensions and one time dimension are intertwined together in a fabric of the universe called space-time, and the shape of this fabric is affected by how much mass there is in the universe. And to illustrate that, let me show you what a two-dimensional realization of the four-dimensional space would look like. If there were no mass, it would be essentially flat. If we go to something a bit more massive than flat, than no mass, say a sun and the Earth, these massive objects will have an imprint on the fabric of spacetime, creating in two dimensions what would look like indents. But if we think about black holes, then these small indents no longer are small, and they become really extremely pronounced. And the reason why this the shape of the curvature of space increases so dramatically is because at the center of this of a black hole we have this exotic point called a singularity, which in theory is a point of infinite density. But about that later. So one of the most important consequences of the curvature of space is that objects or phenomena that we previously didn't associate with gravity at all, or we thought were unaffected by gravity, such as light, because it has no mass, photons have no mass, right now are subject to the same laws that concern planets, stars, moons, and galaxies. So this brings me to a definition of a black hole, which is that black hole is an object so massive and compact that even the light cannot escape its potential well. And if there is one thing I would like all of our listeners today to take away from this talk, is exactly a definition of a black hole. Now, the question you might ask is how compact is compact enough, right? Because we've heard in talks before about the biggest structures in the universe, about the cosmic filaments, the dark matter web, right? But none of that was associated with black holes, was it? So in order to answer that question, I'll bring out another equation, and all you need to take away from that is that the radius at which the event horizon, if you will, the mathematical boundary of a black hole is located, is directly proportional to the black hole's mass, And there is a couple of constants where c squared is the speed of light squared, so it's a pretty large number, and g, which is the Newtonian gravitational constant. So if we take two objects that are pretty familiar to us, one of them being the sun, mass 10 to the 30 kilograms, one followed by 30 zeros, so it's a pretty massive object. And if we take the moon, we've got their respective radii printed in the slide below. And if you wanted to make this amount of mass into a black hole, you would have to squeeze them into, I'll give you a fraction of a second to think of what kind of size you would expect. Well, for those of us who are very quick in counting, you probably know the answer, but for those of us who rather do estimates, I wonder what your answers would be. Had it been a real room, I would have asked you, but because I can't do that, I'll reveal the answer now. So for a solar mass object to be a black hole, it would have to be only 3 kilometers in radius. This is ridiculous if you think about that. And it gets even more ridiculous if you go to the moon, 0.1 millimeter. Can you imagine all of the moon that you see on multiple nights, if they're clear enough, squished into a radius of 0.1 millimeter, less than a tiny grain of sand? Exciting. So as we're talking about sizes, let me tell you about the two flavors that black holes come in the universe. So flavor number one is solar mass black holes, as the name suggests, mass of a few solar masses, and they are scattered. They are scattered all across our galaxy and other galaxies. They are the end product of the stellar evolution, when big stars explode and leave a black hole behind. Now, it is estimated that in Milky Way itself, we've got 10 to the 8 such objects, one followed by 8 zeros. So they're pretty frequent. On the other side of the scale, we've got supermassive objects. When supermassive starts at 10 to the 6, i.e. a million solar masses, and they can go up to, I guess, 10 to the 10, if I remember correctly. And it is estimated, or it was proposed rather, that each and every galaxy in the observed universe hosts one of such exotic objects at their center. And the guys on the left, the supermassive guys, are the stars of the show, the ones that actually got the Nobel Prize awarded. So without further ado, let's go into the prize and let me spell it out for those of you who haven't taken a look at the details yet. So the theoretical part has been awarded to Roger Penrose for the discovery that black hole formation is a robust prediction of the general theory of relativity. So everything is nicely spelled out there, nothing to explain. However, what is interesting is what the title of the experimental prize was, won by Reinhard Genzel and Andrea Ghez. It was for the discovery of a supermassive compact object at the center of our galaxy. I would like to highlight the word compact, which underlines the precision and meticulousness with which the Nobel Committee ensures that the results they publish as award-worthy are correct in the future. Although we are 99.9% sure that the object at the center of our Milky Way has to be a black hole, since if you will, the result is somewhat indirect, we still call it a compact object. So if you're interested in more of the theory rather than the quick rundown that I'm going to give you today, I strongly encourage you to look at the official Nobel Prize webpage, where you will find this excellent summary about black holes, the development of our thoughts, finally through to the experiment. The Nobel Prize Committee has done a wonderful job, so strongly recommend checking it out for those of us who are more interested. But black holes are not as young an idea as we think it might be, because it all started back in the 18th century with two gentlemen, John Mitchell, apologies, no picture here, and Pierre-Simon Laplace, who both around the same time came up with the idea of dark stars. And what I mean by dark stars, they thought of a star that was massive, that was emitting light towards the observer, but was massive enough for its escape velocity to exceed that of light. And what would happen with that ray, which was emitted towards the observer, it would not be able, it would not be able to travel towards the observer because the escape velocity is faster than the speed of light, and hence an object like this would seem to be dark. So that's 18th century. Fast forward more than 100 years, and we're talking Albert Einstein, 1915, proposing the idea of general relativity. And as part of this presentation, I wanted to show you the original manuscript. You can see that it's handwritten. I am not going to attempt the German, I don't know. However, this gives us a flavor of how physics was published back in the day, especially theoretical works. So we've got Einstein publishing the equations in 1915. Bear with me, it was 10 years between special and general relativistic publications. So it took the idea was brewing in his mind for a long while. And then 3 months later, we've got Karl Schwarzschild, his fellow countryman, who publishes the first solution to those equations, assuming spherical symmetry. Unfortunately, in the May of 1916, Karl Schwarzschild passes away, and which comes as a great regret to the theoretical physics community, because one can only imagine how quickly further solutions would have come up had he only been around. Fast forward right before World War II, and we've got Robert Oppenheimer, the father of the atomic bomb, along with his student Hartland Snyder, considering the collapse of spherically symmetric mass within the Schwarzschild solution of Einstein's equations. And the conclusion they draw is that the star thus tends to close itself off from any communication with a distant observer, only its gravitational field persists. And this is essentially the first time when the idea of the event horizon, the mathematical boundary of no return, comes to be in the realm of theoretical physics. So then, of course, the world was a bit more turbulent than we would like, and we've got year 1964 when it was submitted, 1965 when it was published. So Roger Penrose considers the same idea that Oppenheimer and Snyder presented, but this time relaxing the assumption of spherical symmetry, which means, what Oppenheimer and Snyder said, look, we've got a massive star that collapses into a single point, done. Now, one would ask, well, that's very simple. If you've got a spherically symmetric distribution, essentially a ball of mass, it will of course collapse into a single point. That makes only perfect sense. Now, Roger Penrose did relax this assumption and show that no matter the symmetry of the system, all of mass will collapse into a single point called singularity, as shown as the space-time diagram. Time goes upward. Space is this space goes in the x and y directions. So no matter the distribution of mass, it will all collapse into a single point of infinite density called a singularity, which will be hidden in this, again, let me emphasize that, mathematical boundary called the event horizon. Now, coming from Cambridge, we've got it would be just difficult not to mention the fantastic discoveries made later on by Roger Penrose and Stephen Hawking, extending the idea of singularities in the cosmological sense and talking about Big Bang and cosmology as we know it today. So that's the theoretical story. Roger and his word are now on the table, but his formal mathematical proof did not come before an actual experimental observation. So in the slide, I'm showing you a very romantically named quasar, QSL 3C273, which was the first object to be identified as an extragalactic source of extreme brightness. back in 1963, the object was declared as having an underlying mass of 10 to the 9 solar masses worth of light production, and it was found to be outside of our galaxy. And at this point, the whole astronomical mindset about the size of the universe, about our observational capabilities, it starts shifting. We've got an extragalactic object that is so bright as if it was within our galaxy, and hence the origin of all of this light must have been some sort of exotic object. And shortly after, our own Donald Nobel, unfortunately no longer with us, who's no longer with us, proposed that not only is this exotic object a black hole, but also suggested that each galaxy in the universe would host one of those black holes in their own center. Couple of years later, 1971, Donald Nobel and Martin Rees, again, Cambridge, propose an observation that would prove the existence of an object like this right in the center of our Milky Way. So, as we all know, it usually is the case that we've got this brilliant idea, and then technology has to catch up, and that's exactly what happened in this case. So, astronomers at the end of the previous century embarked on a journey to map out the motion of stars around the very center of the Milky Way, where the supermassive black hole is supposed to reside. Now, what I'm showing you in the slide is the map of dust within our galaxy, with the center of with the galactic center located somewhere around that circle. And around that circle, this is an extremely precise map created for us by the Gaia collaboration, which does a fantastic job at mapping the positions and velocities of stars in our galaxy, essentially mapping our own neighborhood with extreme precision. So, as you can tell, it's not really easy to look through this cloud of dust. So, optical observations are out of the window. But what astronomers decided to do is to go into the near infrared at, to be more precise, wavelength of 2.2 micron, where the dust is no longer so problematic, and we can actually trace the positions of stars. Now, this is a story of a beautiful race in science, showing how modern research should really be done. We've got two separate groups at two parts of the Earth who decide to apply similar techniques, observational techniques, cross-checking, cross-validating each other, and proving the consistency of the result they arrive at. This is a beautiful story of scientific success. So what Andreas and Reinhardt's groups decided to do, they decided to use ground telescopes in order to monitor the motion of stars in the galactic center. Now, this is difficult because we obviously have something called atmosphere between us and the universe, which is both a blessing and a curse in one. And in order to get around that, they've used an extremely clever technique of taking very short exposure pictures at timescales much smaller than the turbulent timescale within our atmosphere, hence not allowing the atmosphere to phase out the image. And as a result, sorry for the long chat here, unfortunately I couldn't come up with a very good illustration that would make sense with my PowerPoint skills to illustrate my point. But what they've come up with is that they've measured the velocities of stars next to the galactic center and measured them as a function of distance. So in the vertical axis, you see the velocity of stars, and in the horizontal axis, the distance from the galactic center. And as you can see, as we're guided by the lines in the slide, the velocity, the apparent velocity, falls off with the square of distance, i.e., proving that all of those objects are spinning around a compact distribution of mass. Had all the mass in the center of our galaxy been distributed within, I don't know, a cloud of dark gas, or otherwise undefined group of very dark stars, we wouldn't have seen this behavior. But these plots unanimously show that the source of gravitational potential at the center of a Milky Way has to be a point source or compact enough. So that's the beautiful story of success, and the success has won a Nobel Prize this year, but more importantly, this legacy has been extended into the modern day. So fast forward to year 2018, I'm showing you the results from the collaboration Gravity and the previous results put together. So right now we have this fantastic resolution and enough data to fit the Cyan ellipsis, which shows you the prediction of a motion of a star, again, romantic name SO2, which has an orbital period of roughly 16 years. So this Cyan line tells you what the orbit should look like, including all the general relativistic effects. And indeed, it does match the observations. So yes, we are fairly certain this is a compact object, massive compact object at the center of our galaxy. And yes, we're fairly certain it is a black hole, although remember, the Nobel Prize Committee decided to call it a compact object still. So now that I've told you about the theory and the discovery, the question is, was it all worth the Nobel Prize at all? So this is what Matt referred to as why do we care? And for me, as an astronomer who beginner astronomer who entered the field working with supermassive black holes, I think I can give at least 3 good reasons that hopefully make you think they were worth the prize. So first of all, supermassive black holes surrounded by very luminous accretion disks at a correct orientation emit a lot of light in our direction, and they're called quasars. And quasars are found all across the universe at very distant locations. And not only it gives us an idea of what the universe looked like at those high distances, and exactly, which also means back in time. But more importantly, the light of the quasar traveling between the quasar and us can reveal a lot of an otherwise invisible structure in the universe. And what I mean by this is that if you look at the light from a distant quasar, hopefully the movie loads, fantastic. If you look at the spectrum of the quasar that passes through the invisible gas, neutral hydrogen in this case, as it passes through those clouds, you can see that the spectrum gets covered in a characteristic imprint of hydrogen absorption. Essentially, this neutral gas absorbs quasar light and leaves an imprint on whatever is left to reach us. And thanks to observations like this, we can actually map out the structure of our universe within the line of sight, which again tells us about how the universe evolved as a function of time. Because, as you remember, the speed of light is finite. Hence, the further we look, the further back in time we see as well. So that's reason number 1. There is also a bit more profound general relativistic reason, number 2, which I labeled as black holes being fantastic GR testing laboratories, because really these are by far the most extreme objects that the theory predicts. So if we can get close enough to them, and in this case, I'm showing you a theoretical prediction from the Event Horizon Telescope collaboration, we can predict what the immediate surrounding of a black hole would look like, assuming general relativity, and then compare it with what we actually see. So I'm sure you've seen those images before. They flooded the internet, but I would like you to appreciate how important a discovery this image is. It's not just a picture of a space donut. Actually, the imaging of the shadow of a black hole can tell us a lot about whether or not general relativity is correct, and if not, what kind of corrections suggested may well be worth pursuing. Of course, spoiler alert, the data is not good enough to rule out general relativity, GR standing strong. But if you want to learn more, I strongly recommend visiting the official Event Horizon Telescope webpage, where you will see a lot of good infographics, as well as explanations of how the picture was taken, because that deserves a talk of itself. Finally, the most important reason, at least to me, because that's my field of study, is that supermassive black holes, the ones at the centers of galaxies, are critical to galaxy evolution. And what I mean by this is, if you take a look at those two images on the left-hand side and on the right-hand side, they're both composite images, which means we're not only looking in the optical spectrum, but we're also taking a look in radio and X-ray. What you see is that you have a galaxy, which on the left-hand side is this lovely dusty disk. On the right-hand side, you can't see much because this is an elliptical galaxy. So it looks more like a fuzzy blob. From that galaxy spray out gigantic jets that reach out to distances much further than the size of the galaxy itself. And these jets, well, here they don't look as dramatic, but look at the image on the right-hand side, especially with the red fuzzy overlay. This is in radio, so that's synchrotron radiation, and the galaxy kind of ends here, and the jet reaches all the way out there. So all the streams of energetic, extremely hot particles reach out towards the surroundings of the galaxies, heating up the gas and preventing it from cooling down and forming new stars. Which brings me to the point that the galaxy supermassive black holes, through the varying cycles of activity of those jets being launched and stopped, can potentially remove interstellar gas from the galaxies, literally just blow it away, can heat up the gas surrounding the galaxy and prevent the subsequent cooling and new star formation. And the third point written on the slide is exactly the outcome of these two processes, which in the long run leads the galaxy to stop forming new stars and, if you will, die. But more on that, since this is an area of active research. I have the utmost pleasure of being part of this area of active research. But if you want to learn more about that, strongly recommend joining us on the 18th of November, where James Trussell will tell you all about how galaxies die, and I'm sure he will not forget the supermassive black holes. So at this point, I would like to wrap up the talk, and would like you to take a couple of take-home points from the talk today. First of all, black holes exist. No doubt. Black holes exist, and they're divided into two main groups, categories, flavors, the stellar mass ones and the supermassive ones. The one I'm showing you on the right, actually, cheeky me, I forgot to tell you that I had this joke up my sleeve that you should have probably recognized this image, but Interstellar was published, was in cinemas quite a long while ago, so so maybe this joke wouldn't fly as much. But yes, this is a picture from Interstellar. Second of all, second take-home point, I want you to remember who won the Nobel Prize this year. That's Roger Penrose, Reinhard Genzel, and Andrea Ghez. And the reason why this Nobel Prize came to be is because Roger proved that black holes are the robust prediction of a general theory of relativity, while Andrea Ghez and Reinhard Genzel proved experimentally that one of such exotic objects exists at the center of our galaxy. Finally, I also want you to remember that black holes are really worth the prize, and most of all, they're worth all the fuss that the astronomical community gives them, because first of all, they let us investigate the otherwise invisible parts of the universe. Second of all, they're fantastic GR laboratories. And finally, and most importantly, that's a very subjective opinion I'm giving right now, they are key players in the evolution of galaxies as we know of now. So at this point, I would like to leave you with a simulation of emission of a weak accretion disk around our own central supermassive black hole. And I would like to open the floor to questions, shall there be any?
Thank you very much, Asha. Fantastic stuff. I have to imagine a virtual round of applause happening for you now. I'm sure everyone is very busy in their own homes, applauding hard. Haven't had any questions come through on the chat. I've had some comments saying this is great stuff, so people are obviously enjoying it at home. No questions coming through. I want to give it a couple of minutes. It's not quite as easy as sticking your hand up. You have to type the question in the box. So we'll give you a couple of moments to think of any questions. While they're thinking, can you talk a bit more about how black holes maybe impact your own research? Because your own field of research is galaxy evolution, is that right?
Yes, that is correct. So first of all, I'm actually not surprised that there are no questions asked, because Nobel Prize has been announced a while ago, so I'm sure everybody knows everything about it right now. But
everyone having their minds blown by the incredible science you're talking about, right?
That might be also the case. But coming back to your question, so black holes impact my my research on essentially daily basis, because the question I'm asking is how do these black holes shut down star formation? So the questions I'm trying to ask, is it gas removal or is it gas heating? All the processes that I've described in the slide are feasible processes because they make sense in theory. The question is which one of them wins empirically as observed in the universe. And what is interesting is that there seems to be a general agreement between the simulated and the observed universe. However, the details seem to be strikingly different. And I mean, this is not surprising because whatever you put into your simulation, you kind of get out, but it is not as straightforward as it is for cosmological simulations. But hey, that's another topic. So in short, black holes are their impact on galaxies is my main interest, and more precisely, how they prevent new stars from forming.
So you had a couple of questions coming in the meantime. David Gwynn asking, would it be fair to say that AGN caused the death of galaxies?
Ooh, at this point, I would probably ruffle some feathers in the community. So my belief, and according to the work I'm doing right now, I would say that yes, AGNs do contribute to the death of galaxies. However, they're not the only cause of galactic death. So there might be many ways in which a galaxy can lose its gas, i.e. fuel for star formation, or be prevented from acquiring new fuel. However, AGN for central massive galaxies, if you were to ask me, and I do apologize to everyone in the community, I believe, yes, it is fair to say that AGN do cause their death.
And we've had a question from Daniel Hiller, aged 8, who would like to know, what is the biggest black hole that you know of?
Ooh, that's a fantastic question. So, biggest, unfortunately, I'm not very well versed with actual sizes, but more with masses. So the biggest ones that we've measured so far are probably at the order of 10 to the 10 solar masses. So that's 1 followed by 10 zeros. So that would be 10,000 times more massive than the one at the center of the Milky Way.
Yes, I think it's Abel 45 or something. I never remember. I'm really bad at the names, but no, you're exactly right. Yes, they're absolutely ridiculous, aren't they? Okay, well, so yeah, so many questions coming through now. Emilito 888 asks, have we ever observed a black hole evaporating due to Hawking radiation, or does that take an astronomically long time?
That's a fantastic question. Wow. I mean, the audience have done their research. Fantastic. I love this question. So, so the answer is no. For objects that we can actually observe, i.e., stellar mass black holes, or not to mention supermassive ones, the evaporation process is just too slow. It would take over Hubble time, i.e., the time that passed since the Big Bang to now. So unfortunately, the answer is no, we haven't observed any.
A couple of people asking the same question. Terry Day and Julian Thomas want to know, how far are we away from taking a picture of Sagittarius A star, the one in the center of our galaxy? Obviously, the Event Horizon Telescope took that spectacular picture of M87's black hole. Are we anywhere near being able to do that for Sagittarius A star?
So fantastic question. The images were supposed to come in around the same time for both Star and M87. Actually, Star was supposed to be first, but within their observational cycle, remember that Event Horizon Telescope is not a single telescope. It is actually a precise combination of a giant net of telescopes spanning all across the globe. So they have to come up with a particular schedule. So within their observational window, unfortunately, they had technical issues, and hence they were not able to take good quality observations of Star. So they are right now, as we speak, acquiring data for the second cycle. So if you were to ask me, I would probably give it a couple, maybe 6 months, maybe 8 with COVID, but then I'm not part of the collaboration, and even if I were, I wouldn't have probably told you. So all I can say is stay tuned, because if I were to guess, next year coming in.
Great. Okay, we'll do two more questions, I think, before we switch over to Stargazers. Sharad Pandey wants you to talk a little bit, I guess how much is up to your interpretation. Can you talk a little bit about rotating versus non-rotating black holes?
So, I don't know what exactly. I can't remember the name of the user. What the name was. However, the main difference between non-rotating rotating black holes is that, mathematically the solution is different, but that doesn't tell you much. Rotating black holes can lead to launching of relativistic jets. So these are the guys that you can see in those images. So that's the first difference. A stationary non-rotating black hole would not have that. Another thing is that the size of the event horizon, the location, the distance from the singularity, between the singularity and the mathematical boundary called the event horizon, is smaller for a rotating black hole. And what is fun to talk about, and that's something I think that has been beautifully explained. Yeah, I think I have a resource for you to look up. It's called the Physics Mill, which used to be run by Joanna Miller. He has fantastic explanations of things like that in very straightforward, I believe, language. So please do check this out. But the final thing I wanted to say is that black holes actually, as complex an object and as exotic an object they can only be parameterized by a couple of parameters. One of them being the spin, the so-called black holes have no hair theorem, that the surface of the event horizon cannot be described by any additional parameters, i.e. no hair. That's all of that is explained at the Physics Mill. So I think it's a good resource to go there without me trying to scramble some slides that I don't have right now.
Okay, excellent. So one last question from Matthias, who wants. I wonder why he's asking this. It's very suspicious. He wants to know: can we make black holes in a lab?
Yeah, definitely suspicious. The guy folks day coming up, right? Correct. Anyway, or did I get the reference wrong? I could have got the reference wrong, but
no, it was spot on.
Can we make them in a lab? Well, so I think there was this whole thing about mini black holes being created by a Large Hadron Collider in Geneva, right? That we would be swollen up by those small creations of the collider. Well, the truth be told, these micro, tiny nano black holes, in principle, can be created. So if you will, that's a lab. So yes, they can be created in a lab. However, they would evaporate more quickly than we would observe them. So they pose no threat, and we couldn't really investigate their properties. So sadly, we cannot create a black hole that we would feed matter and see how it grows.
Cool, wonderful stuff. I'm sure Asha would willingly stay here all evening and ask your fantastic questions. Unfortunately, we are going to have to say goodbye, but that means we get to switch to the second half of the evening and switch over to the Cambridge Astronomical Association for some stargazing. I've got my fingers crossed. Are we still looking at clear skies, guys?
Hi, Matt. Yes, indeed. we got quite a good view of the sky. I've got the all-sky camera with not a cloud on it. So hopefully we can go over to Mick and Dave, who are out in their observatories, and I've got a few objects lined up for us. And we've got Brian Lister, who's going to give us a bit of a commentary on what we're going to see. So who would like to go first? Who's got something for us?
I've got Mars up at the moment.
Fantastic. Let's go to Mars.
Hang on. I've got to remember how to switch it over. Have you got my screen?
Not yet.
No, not yet. We can still see ourselves. This is always the
I've
problem of just finding that share screen button.
I have shared it. Oh dear. There we go.
There we go. It's
Is that
coming up.
it?
Oh, there we have it.
Good.
I'll switch it to...
So this is the live view through your Meade telescope at your observatory.
Yes.
The picture's frozen at my end, but
Oh, it's dancing around quite nicely at the moment. Can you see it?
I've got a frozen image right now. Can you move your mouse pointer? No, probably a problem at my end.
No, it's frozen here as well.
Oh.
Shall we go to David?
Yep.
And you have us see if you can sort things out. Okay,
Well,
Dave.
Yeah.
You have to stop sharing, Mick.
Okay, hang on. Let me just sort myself out. If I can. I've lost the button. Oh,
Right, David, can we get you to do a screen share from your side?
Yes, hello. If I
I believe you were on the dumbbell nebula.
yes, this is a window, in fact, with a software called Nino, which is what I'm using at the moment, and I thought I'd do something a little different for you tonight. Last time we met under these circumstances, I used my cooled QSI camera, which is a mono camera, to show you some hydrogen alpha emission nebulae, and thinking in terms of the dumbbell nebula tonight, I thought it would make a change to try and get some color. So this is a rather fuzzy image of the dumbbell nebula, photographed with a ZWO 290 camera. So it's actually a planetary lunar camera, but I'm using it as a deep sky camera. So instead of 20 hours of exposure, I got 20 seconds. If I just get the mount to move a little so we can try and center this object. Come on. I'm taking 20-second exposures, and you can see them counting down in the bottom left here. And I've been experimenting with this in the last sort of couple of hours. I confess I've not tried this before. So this is a first for me too. There we go. And I'll move slightly to the left, slightly down again. The field of view of this camera is really quite small, which came as a bit of a shock to me because my mount isn't very accurate. So finding it is a bit hit and miss. Now this image coming up there where it's a bit more better centered, but you can get an impression of the sort of the gaseous void that this nebula actually is. Normally we look at deep sky pictures of this thing and it looks almost solid, but looking at it tonight under these conditions, and it's very, very faint and tenuous. You can see it there. Can you see that yourself?
Yeah.
One of the issues I have is controlling the black level of this image. So forgive the rather bright black background. I haven't yet worked out how to control that. But I could try and increase the exposure a little more. And
I'm afraid we're running out of time.
Okay,
so
we'll
leave it as it is.
Yeah, I'll leave it as it is.
Yeah. Okay. This is a planetary nebula. It's absolutely nothing to do with planets. It's just that most of these planetary nebulae are round like planets, and they're what has happened to a star, a dwarf star such as the Sun, when they've come to the end of their life. They've thrown off a shell of gas. And you can see the shell of gas. The red colour is hydrogen and the bluey colours are nitrogen and oxygen in the middle. Now, if David can point to the white dwarf star in the centre, that's the remainder. There we go.
Is that it?
I think, or is it the one below? That one. Down a bit, that one.
Yeah.
That's the white dwarf, and that's what's left of the star after it's thrown off this shell of gas. And in this case, it's about half the mass of the Sun, but in 1/500th of the diameter. So it's very, very dense. In fact, a teaspoon of white dwarf material would weigh about 15 tons. And so this will now just cool down for the rest of the time. It's currently at 85,000 degrees. You can see it's slightly blue, and you find that white dwarfs are the hottest stars that we'll see. And this is in the constellation of Optical, the fox, and it was discovered by Charles Messier, who made a list of these fuzzy objects that were getting in his way of observing comets. And so this list we often use, they just have M numbers. So this is M27 or Messier 27. We often use them to look for objects because we find them interesting, but to him they were annoyance, getting in the way of him discovering comets. And it's just over about 1,000 light years away, and it's, to give you a scale, that's about nearly 3 light years across, and expanding at a fair old lick. So it means the whole star erupted, or the shell of material was thrown off about 10,000 years ago. Okay, now we'll go on. And are you going to find NGC 891?
I'm going to go to M15 instead of not M15.
Okay, yep.
Yeah.
It was M13, but don't worry.
I'll go for 15 because I can see that.
Fine.
Yeah, okay, M15. Go.
I was just going to say, Brian, it's gone. I was going to say about the colours that we had there. The outer layer of that nebula is red because it's hydrogen that's from the interstellar gas that's glowing. But most of what you saw in the central core was that green colour, which is the same colour as you get in the northern lights, from the oxygen that's been made in that star. So I see that Mick's gone dark and is on mute at the moment. But if David, if you can move over to your next target, we'll see if Mick's got anything for us.
I'm back on with Mars, but hang on a sec.
Shall we try that while David goes and finds his globular cluster?
Sorry about that. Right. Lost the screen again. Show entire screen, is that correct?
Yeah.
Share screen.
Share screen.
Is it working?
Actually, while we're switching over, the advantage of this YouTube format is that the members of the public get to ask the observers questions as well as the speaker. We've had a couple of people wondering about your optical setup, in particular, what kind of Meade telescope you're using and what your setup is. So can you just mind just saying a few words about your setup before we go to the next target?
But we'll do that once we've got ourselves into a stable state, if that's okay.
Oh, no, absolutely fine. Yeah, just let you know at some point that's convenient. Talking a little bit about your setup. Some people will be quite interested.
Not this week, but in previous weeks we've used my observatory. I've got a 14-inch Meade LX600, which is quite a large telescope. It's a 14-inch diameter mirror with a long focal length, 2.5 meter focal length on it. So it's very good for looking at planets. But the other guys that we've got online tonight are using somewhat different equipment. And we'll get them to say about it at the moment. Mick, you, as it says on the screen, you need to do something.
Is that, can you see that?
I can see it says Mick Jenkins has started screen sharing. Double click to enter full screen mode at the moment from you.
Oh.
So perhaps you'd like to double click.
Is that better? I'm sorry. No.
No, that's come back out again.
Share.
Here we
That's
go.
better.
Does that work?
Right, we've got it.
So over to you, Brian, to talk about Mars.
Here we see Mars. It's about half the size of the Earth, and you can see some markings on it. And if you use your imagination, over to the left, you can see a shape a bit like Africa. And that is Syrtis Major, which is a very dark area on the moon. And it's just above that is a light patch. And that is a huge impact basin. It's one of the biggest craters in the solar system. It's over 2,300 kilometers across. Again, the image is frozen, I think. Yes, it has, because it was wobbly before, but that was due to the atmosphere.
It's still wobbly this end.
No, it's not wobbling our end, but I'll carry on. While we've got this dark smudge, we can see it's generally in the shape of Africa. And at the bottom of this Africa shape is the Jezero crater. That's where Cape Town would be. So on the southwest edge, not too far from the limb. And that's where the Perseverance rover will land in February next year. And it looks a lot like Curiosity rover that landed there in 2013, but it's been seriously updated with 23 cameras, all of them high resolution, even a couple of microphones. And this rover will take soil samples, up to 20 soil samples, which it will leave on the surface of Mars. And then another rover will come along later and pick them up and do a sample return mission back to Earth. So that's going to happen at a much later date. But Mars rotates roughly at the same speed as the Earth. It takes 41 minutes longer. So each time we look at it, if we look at it tomorrow, it will be in roughly the same position. Hooray, we've got it. We've got the wobbly bit back now. No, we haven't. Never mind. So we'll if we look next week, Syrtis Major will be bang in the middle of Mars. And we can't quite see the polar caps, again, because we're looking through quite a lot of atmosphere. Again, it's frozen. So are you ready yet, David?
Yes, I am.
Okay. And are you going to go on to the moon, Mick?
I'm having difficulty with the telescope. It's crashed. I'll reset it and hopefully go.
I'll go on for a bit longer.
David's ready, so let's go over to David.
And let me. I've got a screen full of Zoom, and I don't know how to get rid of it. Let me. I need to have Mick stop sharing.
Yeah.
Hello, Mick, are you there?
Matt, can you make me co-host?
And just bear with me.
Thank you.
You are now co-host.
Right, David, you're up. Try sharing now.
Thank you. Let me exit full screen on that, and I can bring up Nina and share.
Here it comes. Splendid.
So this is Messier 15. It's about 2/3 the size of M31 that we, not M31,
M13.
M13 that we were after earlier, but unfortunately M13 is behind my neighbour's trees.
Okay.
For interest, we're viewing this with an 8-inch Ritchie-Chrétien telescope.
What sort of focal length have you got there?
I've got a, natively it's 1.6 meters, but I've got a reducer on it to increase the field of view, and it's 1.1 meters.
That's not too bad then. Right, so we'll just get Brian, are you fit to commentate on this one?
Yes, don't mind a change of plan. Okay, it's over 30,000 light years away, and these globular clusters, as you can see, are just a ball of stars. In this case, there's over 100,000 stars in this ball, and it's there's about over 150 of these globular clusters that we can see around our galaxy. They're not part of our galaxy, they just swarm round the galaxy like bees around a honeypot. And to give you a scale, this is much, much further away and much bigger. We saw that the Dumbbell Nebula was just 3 light years across. This is over 175 light years across. So the whole ball is like almost a mini galaxy. So these are very old clusters. In future weeks, we'll look at the other sorts of clusters that are inside our galaxy. But for now, we're looking at these globular clusters, and you can see that that's just the new image being refreshed. Every so often, you'll see the image refreshed, but it will sort itself out. How long's the exposure, David?
David's on mute, but
got
it
it.
take about 20 seconds.
20 seconds exposure, I think.
Yeah, that's it. We can see it refreshing every
Right.
20 seconds. That's good. It has to do. It has to go on that long to store up the faint light so we can see it. If we had a much shorter exposure, we'd only see a little ball in the middle. And these are very old clusters, as I was saying, and they don't have hardly any gas, or they're just made up of very old stars. They can be sort of 13 billion years old. And when you consider that the universe is only less than 15 billion years, you can see just how old these globular clusters are. And
there's something unusual about the center of this one, isn't there,
yes,
Brian?
yes, the Uhuru satellite way back in the 70s, and certainly Chandra and other X-ray satellites have picked up X-rays in here, and over half the mass of this globular cluster is in a very small space, just 10 light years across, meaning that there is a black hole in the center of this globular cluster. There are about 20 globular clusters with this very compact nucleus of stars, and most of them are figured to be black holes. So there's an active black hole right in the middle of this globular cluster. So that's that. Unfortunately, you just can't see black holes just yet. But as our speaker said, we hope to have an image in maybe next year.
But this particular one, these globular clusters is intermediate mass, isn't it? It's bigger than a typical star-sized object. It's a typical stellar mass black hole. But much lighter weight than the ones we find in the center of galaxies. Do you know roughly what the mass is? Is it, we're talking about 1,000 solar masses or something like that?
I don't know that number yet.
It's of that order, I think.
Yeah, it's not a huge number.
And how many stars are there in one of these globular clusters?
This one is about 100,000. We were going to look at another big one in Hercules, which had over 300,000 and is the biggest globular cluster in the northern sky. But unfortunately, trees are playing havoc with David's view.
Neighbours will have trees, won't they?
Yeah. What we do with a chainsaw, eh? Okay. How's Mick getting on with the moon?
He's on mute. He'll have to unmute himself if he's going to talk to us. And then, David, have you got a third object that you're going to be able to find for us tonight?
891.
891.
Okay. Well, if you'd like to unshare and head for NGC 891, the Outer Limits Galaxy. I know it's 27 million light years, but you'll get there in no time, won't you? We'll see if Mick's got anything for us. He was having issues with his telescope. So,
it's crashed.
And he's still on mute, so I don't know there.
We were going to look at the moon, but it's well placed at the moment. But by next week...
Just while we're waiting for Mick to unmute himself, can you see the all-sky view there? So we've got not a cloud in the sky, and the very bright thing down at the bottom here, this is where the moon has just risen as viewed by the observatory. And we've got quite a few stars in the sky. This is the constellation of Cygnus up here, where we were looking, and the Dumbbell Nebula was roughly there in Vulpecula. But I'll come back off there, and we'll give Mick a chance to rejoin us. Mick, are you able to show us anything? I've got two versions of Mick online with us now.
Yeah.
This is not good.
Can't hear anybody.
Oh, I can hear you, Mick.
Yeah, Mick.
That's David's observatory dome rotating that we're looking at there. So it's obviously changing targets and heading for this galaxy that's it's in Andromeda, but it's not the Andromeda galaxy.
No.
The Andromeda galaxy is always a good target for binoculars, but
Can you hear me? Anybody?
We
Yeah.
can hear you, Mick. Yes, you're back in the room. Can you hear us?
Did you manage to find the moon, Mick?
It's not clear that he can hear us.
No. A few technical hitches, but never mind.
We'll get good at this one day.
One thing we had planned tonight was that there was a look at a double star, and there was going to be a piece of space junk go across the double star, a piece of Chinese rocket. But unfortunately, Mick's telescope couldn't get on that particular double star, so we've had to give that a miss, but we'll try it again another week. Meanwhile, I think David seems to be happy.
No, I'm now struggling with the inaccuracy of my mount, which I mentioned.
All right. Well,
and I've gone to a bright star, which I hope it will tell me which way I need to move the telescope to get the thing in the field of view, and then that will give me a clue what to do with the galaxy. So I would hope to be able to see a bright star. So I'm on Gamma Andromeda, but there are very few stars around it.
Well, Gamma Andromeda
that's the one we were after.
That's the one we were going to have the piece of space junk cross.
Oh, right.
Have a look at that.
If you want, we can have a look. Yeah, go for it.
Well, it's out of the field of view of my camera at the moment, and I'm just going to play with this for a few moments.
Okay.
What I need to do to bring it into view. This is a game I play before plate solving came on the scene.
Things are very different on the lawn of the Northumberland Dome when we're doing observing at the Institute, because we've got 4 telescopes, so we've always got something to see. So we've got 3 large screens and 4 telescopes, so we can always got something going. But at the moment we've only got 2 telescopes and one of them's playing up badly.
I'm back. Can you hear me, Brian?
Yes, we can hear you.
The telescope's completely died for some reason.
Okay. Well, don't worry. We'll go back to David and we'll see whatever he can find, whether it be Gamma Andromeda or the galaxy.
Right, I've got Gamma Andromeda I can show you, and then we can have a bit of fun together. I'll swing to the galaxy and see if, here we are.
Right.
I think that's it.
Yes, and if you increase it a bit, can you increase the gain a bit?
I can put the exposure up.
What is the exposure at the moment?
5 seconds.
Oh, that's okay. We're okay. We can see the companion star. Now, this main star that David's pointing to is a red giant star. It's dying. It's much less massive than the sun. It's about 3/4 the mass of the sun, but because it's run out of hydrogen, that's how stars work, turning hydrogen, fusing hydrogen into helium, and the star has swollen up in this process of dying. And if we were to plonk it where our sun was, it would stretch out to the orbit of Venus. So this star is truly enormous, but it's also very tenuous. And then just at 5 o'clock, we've got its companion, not that one, that one. That's it. And you can see that looks a little bit blue. And that is in fact two very hot stars orbiting round each other in less than 3 days. So we can't see them. Obviously, well, they're too close to be seen with the telescope, but they're so close, they're whipping round every 3 days. And then those two stars are going round an even hotter star every 64 years. So that single point of light is 3 stars, 2 whizzing round each other and then taking a more leisurely trip round a brighter star. And those 3 are orbiting the dying star in about a 5,000 year orbit. So it will take 5,000 years for the little blue triplet to go round that giant star. It's quite a nice color contrast. If you get to look through a telescope, you can see the blue and the red color. We're not getting much of the red color from that giant star. And that is about 350 light years away, so a comparatively near star. Okay, do you want to go on for the last object of the galaxy now, please?
Yes. Now, here's a little trick I do. I've got Carter-Seal sky chart here, and what it's showing me is where Gamma Andromeda is relative to my field of view. So if I turn the red thing off, and you can see it's somewhat just off the center. So hopefully I can, by making the same move with the telescope, I can find 891, which is down here. And if I telescope and slew to that,
everything will blur.
And here it comes. Hopefully.
Because both these are in Andromeda, so they're not very far away, so the telescope doesn't have far to move. We're still getting movement of the stars.
Yeah, I'm moving the telescope to the right.
Yeah.
To try and capture this. Now what I should do is put up the exposure time.
Yeah. What to again, about 20 seconds?
Back to about 20 seconds, are we?
Yeah.
What's this?
Yeah.
Yeah.
Stop there.
Yeah. Well done.
Now give it the beans.
Right, let's put up the exposure time now. Back to imaging, stop the camera, change that to 20. Turn the camera back on and go back to the image.
Fingers crossed.
Fingers crossed, this is it. Looks a bit round to me.
Yes, it does. I think
that's because it's not the galaxy.
That's a star, that is.
Let's just check where it is in the sky chart. Center this.
This is quite a tricky object to find sometimes. But I think that star that you're looking at is in roughly the right star field.
Yes. But fortunately, the galaxy itself is quite big. So
yes.
if we even if we've got a fraction of it on the screen, you'll soon see it.
I did have a look at it last night, and
is that a bit of it at the top left of the? Yeah, up there, right at the top of the field.
There.
that bit.
Yeah.
Right, let's try and bring that down.
Yeah, I think we're giving a very good demonstration of why astrophotography is a lot more difficult than you think.
It certainly is. I've spent many nights sort of trying to find my way amongst the stars, trying to plate solve the sky myself. And it's really quite tricky.
Yeah.
Come on.
Is the sky misty at all out your way?
No, it looks quite clear out now. Of course,
right.
we've got the moon there.
There's a certain amount
right.
of moonlight, isn't there?
Yeah, that's going to hamper things a bit.
But the stars are coming up quite clearly.
Yes, yes.
I'm moving to the right again a bit more. See if I can. And unfortunately, I'm now dealing with the camera, which is a very narrow field of view.
Yeah.
Being a planetary camera, so come along. See where we are. We're about in the right place. I just checked the sky chart again. Let's go down.
I can't see anything in there at all now.
No.
No.
Well, we'll give it a couple more minutes and then we'll call it a day.
What I could do, it occurred to me earlier, is look at something like M110 next to Andromeda, because it's a much bigger target.
Mm.
Well,
we're coming to the end of our time, so
we are, yeah.
Yeah. Just give it another minute or so, and then we'll. But we've had some successes.
Yes, but I could go there fairly quickly if you want to try it.
Okay, well, just give that a try because this is not getting us anywhere. So
no,
we'll make that the last attempt then, and swing over there as quickly as you can. This is one of the problems with these go-to telescopes that the press love to try and sell you as naive observers is that they will simply point and find their way directly to an object. And I think what we're showing here is even with an expert observer like David driving it, we just can't. Hello, Mick, are you back?
Yes, I'm back.
Have you got anything for us?
No, the telescope's completely dead.
Okay.
No, don't worry. We're just going to have a last. And did he say it was Messier 110 you're going for?
Yes, that's what I was hoping to see.
Yeah. This is a dwarf elliptical galaxy, and it's a satellite of the Andromeda galaxy. And of course, the Andromeda galaxy is our neighbor galaxy, about 2.5 million light years away. Us and the Andromeda galaxy are the main two galaxies in our group of 30 or more galaxies. But just as we've got two dwarf galaxies, the Magellanic Clouds, which can only be seen from the southern skies, the Andromeda galaxy has got a couple of small elliptical galaxies as neighbours. And we're looking at the Messier 110. And it was discovered by William Herschel's sister, Caroline. We always hear about William Herschel's discoveries. After all, he found Uranus. But his sister was a keen observer as well, and she discovered quite a few comets, as well as several of these faint fuzzy objects. And this is one of her discoveries that she made way back in 1783. So it's considerably less massive than the Andromeda Galaxy or the Milky Way. And it's slightly flat, as you'll see.
Well,
it's not but it contains a lot more stars than a globular cluster, and it's much, much bigger. The Andromeda Galaxy has got about 500 globular clusters compared to 150, as I mentioned. But we've just got to wait for this to come up now.
Come on. I'm still not seeing it.
It goes to show how small the field of view is, I think.
It is.
And just how accurate you have to be.
I could be brutal and just go for M31.
Yeah.
I think we wouldn't notice it.
No,
It's just your field of view completely 50 times over.
It would, absolutely.
Yeah, it covers 4 degrees of sky, and a telescope like this only covers a fraction of a degree. So actually, the Andromeda is best seen in binoculars rather than looking through a telescope, because all you can see is the fuzzy blob in the middle, the nucleus of the galaxy.
Yeah, well, I think we've probably reached the end of our time, guys.
We have now.
Yeah.
So thank you so much for your
trying.
efforts. And I think we'll draw this to a close. We'll have a bit more of a practice and try and get a bit slicker at doing this for next time. Hopefully I'll be back in the loop with my telescope.
Yeah, three telescopes will be better than 2.
I'll have to get plate solving going, because that would solve this problem.
Right. We'll hand over back to Matt now.
Wonderful. Thank you very much, guys. Yeah, some fascinating stuff. I absolutely love these views of Mars. We've had some amazing views of Mars over the past few weeks. So yes, lovely stuff as always. Oh, getting a lot of echo from someone.
Probably me.
I will mute everyone. Yeah, so just to wrap up and say thank you very much to everyone, to Asher, who was our headline speaker, and to the CAA. And yeah, we will see you next week. Cheers. There we go.